Welcome again. There is yet another problem needs to be solved, and it says at the end of a weightless rod. This rod is weightless, okay, of length L, pivoted to a wall. I can see that there is a load of mass M. The rod is held in equilibrium in a horizontal position by a spring of a stiffness constant K. It must be stretched attached to a distance L1 from the hinge where the angle between the spring and the rod is equal to alpha. Okay. Find the frequency of a small oscillations of the load relative to the equilibrium position. So we have to find out the angular frequency of for the small oscillations of the load. Okay, and this is the equilibrium position. So what happens next? I have a picture drawn. I just drawn this picture, and you can see this picture. It happened. That means this picture says the load is displaced from this position to this position by an amount x, and the length of the spring in equilibrium position was x naught. I don't know I'm trying to say you the total length of the spring in equilibrium position was x naught, and the total length of the spring after the load has been displaced by a distance x, the length of the spring has become x1. Yeah, this one. And you can see that the amount of displacement of this junction point of the spring and the rod by x dash, and that means I don't know what will be that means elongation of the spring during this process is delta x. So we don't need to consider the initial condition of the spring was stretched, because it is the change in length of the spring that causes the force. So the spring will apply a force, and we know this. And what can we do next? The problem is this. We have explained everything, but just planned the things, but how are we going to solve this problem? I'm interested since all the extensions, this thing, and this x1 length is slightly greater than x naught. That means is this length x dash is quite small, and also the x. These things are quite small, and that makes me assume that I can strongly assume that this length you can take as a perpendicular. Well, everything here is rotating in a circle. I know. Everything here is rotating in a circle, moving in a circle. And this is a very small angle. Call this d theta. That means x dash being very small, and so will be x. And then this angle will be 90 degree, no problem at all. And after considering all these things, we can apply a sine formula to this triangle. The name of the triangle being ABD. Yeah, I can use a cosine formula, cosine law, a cosine formula, whatever you wish to tell it. So I'm going to write the cosine formula as cos pi by 2 plus alpha is equal to, this angle is pi by 2 plus alpha. So I'm going to write down, this will become x naught square plus x dash square minus x1 square divided by 2 x naught x dash. Yeah, so I can write here minus sine alpha, that means 2 x naught x dash minus sine alpha will be equal to x naught square plus x dash square minus x1 square. So that I can write here x1 square equals x dash square plus x naught square plus 2x naught x dash sine alpha. Yeah, I can write it here. And now what? Now what can I do? x1 is this length. Okay, x1 is this length and x0 is this length. And I can write one thing, that x1 minus x0 is equal to delta x, the change in length of the spring. And I could write here one more thing, that x1 plus x0 is approximately equal to 2x0, because this angle is very small. So I can use it. These two statements seem contradictory. In that case, you will call it x1 minus x0 will become 0. Yeah, delta x is very close to 0. It's not exactly equal to 0. So this relation can be used, x1 plus x0 equal to 2x0. And I'm going to use them. x1 minus x0 equals delta x and x1 plus x0 equals 2x0. I need delta x because, so I'm going to write it, what was it, x1 square minus x1 minus x1 square minus x0 square equals x dash square plus 2x0 x dash sine alpha, and that means x1 minus x0 and x1 minus x0 is delta x. So it's delta x, and then x1 plus x0, that is 2x0, x1 plus x0, 2x0 equal to x dash square plus 2x0 x dash sine alpha, and x dash is quite small. X dash length, this length is quite small. So x dash square is 0. That means x dash square is 0. Oh, where is x dash square? Oh no, something mixed up. X dash square is 0. I'm going to write down, this was x1 minus x0 and that was delta x. x1 plus x0, that was 2x0 equal to x dash square plus 2x0 x dash sine alpha. And I'm going to put down x dash square equal to 0. X dash is quite small. So I have the result 2 delta x x0 equals 2x0 x dash sine alpha, and 2 x naught gets cancelled out. I get delta x equals x dash sine alpha. And there is a problem. What can we do about x dash? We can do one thing. This angle is quite small, so we can write something here like focusing on this angle, that this length is L and this length is L1, and L you can remember, so I can write this is the arc length. So I'm going to use L equals R theta. That means x equals L d theta. I can write here x equals L d theta, and x dash equals L1 d theta, and then I can write x upon L equals x dash upon L1. Yeah, and then I can write here x dash x L1 equals x dash L. And how can we use this? X dash, we need to find out x dash. X dash equals L1 x by L. X dash equals L1 x by L. So x dash I'm going to write here x dash equals L1 x by L multiplied by sine alpha. So I get the delta x from here. It is approximately equal to this. And I'm going to write down the mechanical energy conservation, which is the key to solving this kind of problems. And after getting displaced, after this, when the spring was stretched by this length delta x, the load got a velocity v at that moment, and the mass of the load is given. So I can use at the cost of half k delta x square, our load gets the velocity half mv square, and half kx square is simply k delta L1 sine alpha by L square multiplied by x square equal to half mv square. And I can differentiate it with respect to time. Now I want to differentiate it with respect to time, so that, and where is 2? Where is 2? Yeah, 2 must be here. Perhaps I forgot in a hurry. It must be. And eventually they will get cancelled out. And after differentiating, I can write here k L1 square sine square alpha. Alpha is a given value, so it's a constant L square 2x dx by dt equals m 2v dv upon dt. And again I can say here that v is equal to dx by dt. Here v is dx by dt, and we can cancel out both of 2 and v, and we can write the equation as dv by dt equals k upon m L1 square sine square alpha by L square multiplied by x. and you can find your omega, the angular frequency that was required, and that will be under root k by m L1 sine alpha by L square. And I think I solved the problem. You may find a better way to solve this. I thought I solved the problem. Thank you very much for watching. These are hard work. Thank you very much.